Okay, let's take a look at section 3.9 on linear approximation in our study of calculus. Today what I'd like to show you is a pictorial representation of local linearization and then hop into a Desmos-aided graphical representation of what's going on here. Then we'll talk about the algebra and I'll give you one good example of this phenomenon. So here we go. This is the pictorial representation, what we can think of as pictorial representation of a local linearization. So what we have here is a function. Let's a periodic function drawn in black. So it looks like the sine curve, and we are looking at a local linearization of the sine curve at the value of x equals 0. In other words, in the neighborhood of 0, we've attempted to approximate the function using a line. That's what a local linearization is. And we can see that as we zoom in, other way, on the value at x equals 0. Now we're looking at a window that ranges from +2 to -2 in both directions. That the local linearization does quite well, especially in the region around 0. If I zoom in one more level, then I can see that, in the 1 by 1 view, so +1 to -1 in both directions, that the local linearization, that is the red line, is a very good estimator of the function itself. So really what we're talking about in the context of calculus is the any function, if we think of it in a zoom-inable sense, that if we find the equation of the line that is tangent to the function at a point, then we've got a pretty good estimate of what the function's doing in the neighborhood of that point. So in other words, we can use a line to estimate the behavior of a function in a very local sense. So once again, look at this from, this is not local at all. It's a very global view, but as I get closer locally, I can see that that function is behaving like a line. Okay, so let's take a look at what Desmos can show us about this. I'll go ahead and get myself in projector mode. And here's what we mean by local linearization. Basically what we're talking about is the equation of that tangent line around this point A that I've chosen, that I can kind of scroll around as I want. Now I can see that that line itself has grows quite a bit away from the function if I'm on one of these points of high curvature. In other words, if I want to sort of quantify the error, here I'd have to consider local linearization only to be valid in a very, very local sense, somewhere in the neighborhood there, very locally. Whereas I got farther away, if I was a whole unit away, I would think, oh, that's not representing the function well at all. So very locally here around this high curvature point, I would think that I would be valid as a local approximation or have fairly high degree of accuracy only if I was within about 0.1 to the left and to the right of the value of A, which I've chosen at -1 here. So in that spot, it's pretty hard to build, I guess, a case for local linearity that's accurate for a distance around A much larger than that value. Now, of course, the situation is very different if I choose this point, at a different spot, say at 0. There I can think, wow, locally it's behaving like this particular black line. The blue function is behaving like the local linearization in black, out to even 0.5, 0.6 away from that value of A, which is 0 here. So we're getting some error here and some error here, but it's much more forgiving, I guess is what I'm trying to argue, when we choose A to be 0 at a spot where things are not highly curved. So you can see that the local linearity has a lot to do with the value of the second derivative, the degree of concavity at the point A. So just some ideas there, I guess, to think about. If we maybe scrolled this over here, we can see that again we're in a spot that's it's not very forgiving. We get high errors as we look at the difference between the function and its local linearization. But if we scroll this, say, out to, I don't know, right in here, we can see that the errors are not so great anymore, and I'd be comfortable saying, much higher degree of accuracy, or maybe another way of saying that is the function itself is more linear in this neighborhood than it was in the previous one. So I hope that gives you a sense of what we're talking about from a graphical standpoint. let's go ahead and continue on and algebraically derive the representation. And so it turns out that the tangent line to f passing through a comma f of a can be used to approximate the curve of y equals f of x when x is near a. And this equation is given by this particular formula, y equals f of a plus f prime of a times the quantity x minus a. So we say a linear approximation of f near x, a linear approximation of f for x near a is given by this. F of x is approximately equal to f of a plus the derivative of f at a times the quantity x minus a. This function is called the local linearization of f near x equals a, and L of x is equal to f of a plus f prime of a times x minus a. Why is that true? Well, I hope you asked that question. Let's go ahead and talk about that. Where does that equation come from? So what do we have here? We have a situation where we have a function and a point on a function, and we're trying to find a general equation for the tangent line to that function at that point, right? That's really what's going on. So if this is my x and this is my y equals f of x, then what do I have? I have some function. There it is, some function f of x. And we're interested in what the function's doing around the point a comma f of a, right? So that's the value of that point, a comma f of a. And we know that from calculus and from looking at these pictures that things in this neighborhood behave, well, kind of linearly, right? So we have some line that we would think would be within this little region in there is behaving very much like the function. So that's L of x. And what we're after is a general form for the equation of L of x. So off we go to the races. What is L of x? Well, L of x right away is a line, right? It's mx plus some b, right? And we know a little bit from calculus to get us help here. We know that the slope of f of x, right, at the point A is equal to the derivative evaluated at A. So f prime of A times x plus b will be one way we can quantify that slope. Now the question is, well, what's b, right? And the way we usually find b in these settings is we plug in a value for y and x and solve for b. So here we go. If the value of the function is f of a, what we have here is for y of x, we'll plug in f of a. That's our x comma y value, right? And that's equal to f prime of a. And then for x, what we'll plug in for value is a. And then we add b to that. And what we're trying to solve for, of course, is b. And this implies then that b is equal to, it'll be f of a minus f prime of a times a. Okay, so what does this all get us? Well, that tells us what b is. We know what m is. It's right there. So I'll plug b in where it should be. And so that this gets us to an implied statement where L of x must be equal to f prime of a times x plus b, which is f of a minus f prime of a times a. And I'm noticing now that I've got two f prime of a terms. Let's factor those out of those two common terms and leave f of a out in front. So this is L of x equal to f of a, this term out in front, and the f prime of a's factor out, and I'm left with an x from this term and an a from this term. And I believe that is the definition that we provided in the previous slide, that the linearization at x, the local linearization of the function near x equals a is given by the value of the function at f at a plus the derivative at a times the quantity x minus a. Okay, so it's a nice result. Some things that you might notice here is that the linearization at a is perfect if we plug in an x of a. So if we evaluated it at a, what we get is L of a equals f of a, and an a minus a guarantees that this is 0. So at a, the local linearization is equal to the function at a. Now away from A it's not quite, and the difference is determined by the slope of the function at that point and how far away we are in terms of x from the value of A. So local linearization L of x of a function f of x at x equals A is error prone as x moves away from A. The error in the approximation, E of x, is defined as the value of the function minus the value of the local linearization. So we could also quantify that as the value of the function minus the definition of the local linearization. Let's take a quick look at what that means when I look at our picture of that. So what is the error? Well, the error would be something like this. For some value of, well, for any value of x, right? We can see that this quantity right here is the error associated with x because it's equal to the value of the function. So this distance is equal to the value of the function minus the value of the local linearization. So that little bar there would be the error between the function and its local linearization for some x here on the x-axis. So that would be, maybe I shouldn't use x since I'm using x as a variable. Maybe we'd say that's the error at b, where b is the value I'm interested in here. Over here we could look at the error at some value of c, right? And the error in c would be, this distance right here, which again is the value of the function f evaluated at c. Minus the value of the local linearization, so L evaluated at C. You can see that the error can be positive and negative depending on which of the functions, I guess, is on top, whether the function or its local linearization is greater in magnitude. Well, let's do a quick example. We want to show that e to the negative x is approximately equal to this linear function, 1 minus x, near the value 0, and determine the domain over which the error in this approximation is less than 0.01. Okay, so we got to figure out where this function can be locally modeled by this function, how far out that approximation works in terms of minimizing error less than 0.01. So a quick picture on Desmos might help. So let's go there first. Let's throw in our function. This is going to be e raised to the negative x. Let's go ahead and sort of turn some things off just so we have a picture of the function. I'm going to get rid of a and all these other things. Okay, so we've just got our function. The other thing we want to add in there is we want to add another function y equals 1 minus x. And now I can see kind of what we're getting at, right? We're looking at the fact that the red function is a pretty good estimator of the blue function, the red function, of course, being the local linearization. And I'm looking for, where the error is, well, less than the desired quantity. It's kind of hard to tell here, but if this is the value of 1 and this is 0.5, then each one of these is a tenth. Going back to the statement, I'm looking for something where the error in the approximation is less than 100th, right? So I must be in a very tight band here because, I mean, out here I can see that the error is about a tenth. Out here I can see that the error in this region is about a tenth. So I'm looking for 1/10 of that error. I'm thinking that the domain is very close to sort of negative 0.1 to 1.1 or something like that. But let's first show that this is indeed the local linearization using the definition. So let's go ahead there first, and then we'll do the error analysis second. So off we go. Okay, so let's see. What we want is we want to show that e to the negative x is approximately equal to 1 minus x near x equals 0. Okay, so our proof is as such. If we want to show that's true, we'll just say that f of x is equal to e to the negative x, right? By the way, that implies that f prime of x by the chain rule is e to the negative x times negative 1, which is negative e to the negative x. We can then state that the local linearization of f of x near x equal to 0 is given by L of x, where, well, what do we know L of x to be? Well, L of x is, by definition, equal to f of a. I mean, what's a? We have to decide what that is, times f prime of a times x minus a. Okay, so in the definition, A is usually the region where we're linearizing, or the region we want to be close to. So in this case, A is 0. So here, A is equal to 0. So we have L of x equal to f of 0 plus f prime of 0 times x minus 0. Okay, so now we can get someplace, right? So what is f of 0? Well, when I plug 0 into f of x, I get e to the negative 0. Anything to the 0 is 1, so it's 1 plus. Now, f prime of 0, if I plug a 0 in here, I get e to the negative 0. That's 1, but I have a negative there, so it's a negative 1 is my f prime of 0. And then x minus 0. So it looks like what I have here is 1 minus negative 1 times x, which is just simply 1 minus x. And so we've shown that near x equals 0, what do we have? We have e to the negative x is approximately equal to 1 minus x. And why is that true? Well, because e to the negative x in our setting is our f of x, right? And 1 minus x in our setting is equal to our L of x, and these two things we know to be roughly equal near x equals 0. So that's really what we've just shown. We've shown that the two functions behave very closely to one another in the region near x equals 0. So now the question becomes, what about error analysis? Well, let's find out the error analysis. So let's take a look at the error of x and just use our template here. The template says the error associated with the local linearization is f of x minus L of x, right? So in this case, f of x is e to the x minus L of x is 1 minus x. And what do we get? We get something that looks like, let's see, so it'd be e to the x plus an x and minus a 1. And what are we trying to do? We're trying to find a value of x such that this error function is less than 0.01. So we want to find x such that e to the x plus x minus 1, okay, is less than or equal to 0.01, right? Now this is a situation where I think technology will help us solve the question. So I'll just go ahead and swap over now and take a look at technology and see if we can get a value here. So let's see. Actually, I'm kind of seeing, let's see here, escape. Let's get out of here and let's go back into Desmos. And what do we want to plot? Well, I'm going to go ahead and start by plotting the function that we're trying to get underneath. So e to the x plus x minus 1. All right. Oh, sorry, I have a little error, don't I? The value of the function is e to the negative x, isn't it? So I've got a little error. I just will correct it once we go back to the screen. Sorry. So that's the value of the function e to the x, and we want to know the difference between it and the value of the local linearization, which is 1 minus x. So there it is. Let's get rid of the local linearization itself, so it's out of there. And I can see I get something that sort of makes sense to me, that at the value of 0, the difference between the two is actually 0, which is as we would expect, right? And I guess the other question would be, well, where is this thing under the value of 0.01? So what I would just plot at this point is y equals 0.01, and I can see that that's this line in here. I'll make it a different color just so we can see it. Make it black, and I can see that in this region right in here, I'm actually underneath. I really need to change my graph settings because I've got it so squashed that it's really hard to see. So I'll start from negative 0.02, and I'll run it to positive 0.02 as well. And this is what you see when you run it this way. This is actually the value of the error function, but we're in so tight, right, that it's really hard to see. I guess it makes it look kind of parabolic in form. And what I'm really after is that point right there. I can see that at about an x value of 0.1448, I get an error value of 0.01, and an x value of negative 0.1382, I get an error value of 0.01. So in the sense, if I'm looking for a domain where the error, the value of the error, which is this blue line, is below that, I would take this x value, negative 1382, and the other x value, which is 1448. So I will go back to my image here and just sort of remind myself what's going on. 1448. So I would write something like, via technology, I found that for the interval 0.1448, and I guess on the negative end we had what did we have on the negative end? Negative 1382. The error is less than, running out of lead here just in time, 0.01. So that's the way I would interpret, I guess, the error in this sense. So you can see that in terms of having an error that's very small, less than 1/100th, that the local linearization in that region is with, under that threshold of error. And that concludes the example that I have for you. I hope that you learned a little something about local linearization, and we'll end it there. I hope that you have a good sense of section 3.9. Look forward to seeing your homework on this section.